Good morning. This is the fourth class of rotational motion. So, in today's session, we are going to find the moment of inertia of a thin circular disk. Okay, consider a uniform circular disk of mass m and radius r. Let m by pi r square represents mass per unit area of the disk. Pi r square is the area, right? So m by pi r square will be the mass per unit area of the disk. Let it be represented by the letter sigma. Now we are going to find moment of inertia about an axis passing through the center and perpendicular to the plane. Okay, here as per the figure, z dash is an axis passing through the center and perpendicular to the plane. Now this is a circular disk, right? Now here we assume that this circular disk is made up of a number of concentric thin rings like this. Okay, a number of concentric thin rings will form the circular disk. Okay, concentric means concentric rings means rings with the same center. Okay, now consider one such ring. That is, we are assuming that the circular disk is made up of a number of thin concentric rings. Now we are going to consider one such concentric thin ring. Let its radius be small letter r and thickness dr. Okay, in the figure they have shown it like this. See, this is a circular disk and this is inside that you can see one more ring, right? This is the thin uh, concentric ring that they have considered of radius r. Radius is marked there and thickness small letter dr. That is, see, you can see one portion, shaded portion inside like this, right? This one. Okay, now that thickness is dr. Okay, now what will be the area of the ring? It will be 2 pi r dr and mass of the ring will be 2 pi r dr into sigma, that is mass per unit length. Then moment of inertia of the ring about z dash will be 2 pi r dr sigma into r square, because moment of inertia is mass this one into distance square r square. That is why r square is written here. So on simplifying this one, it will be 2 pi r cube sigma dr. Okay, that is a moment of inertia of the ring about z dash, that is about an axis passing through the center. Now that is the moment of inertia of a small element, that thin concentric ring. Now in order to find the moment of inertia of this circular disk, what you have to do, as I said, you have to integrate this from 0 to capital letter R. Why? Because the radius of the circular disk is capital letter R, that is this one. From the center it is R. So you have to integrate from the center to this one to get the moment of inertia of the whole disk. That is why you are writing capital letter R. Then apply integration. 2 pi sigma is taken outside. Then what is integral r cube dr? R raised to 4 by 4. Apply the limit 0 to r. Now 2 pi sigma is, we have already written, it is m by pi r square. Then this one is, after applying limit, it will be r capital R raised to 4 by 4. On simplifying, you will get the expression for moment of inertia about the center as mr square by 2. Okay, now we are going to find moment of inertia about diameter. For that, as explained in earlier classes, we are considering two mutually perpendicular diameters, say xx dash and yy dash. Let moment of inertia about xx dash be ix and let moment of inertia about yy dash be iy. As already discussed, the moment of inertia of the disk about any diameter will be same. That is, ix will be equal to iy will be equal to moment of inertia about diameter id. Now you just apply our perpendicular axis theorem. Then moment of inertia about z dash will be iz equal to ix plus iy. Since ix is equal to id and iy is also equal to id, iz will be 2id. So what will be ID? Iz by 2. The expression for Iz we have already derived. What is Iz? Moment of inertia about an axis passing through center. We have derived that expression, that is mr square by 2, right? So just substitute the value of Iz as mr square by 2. So your ID will become mr square by 2 divided by 2, that is mr square by 4. Okay. Now next case we are going to take an annular disk. So consider an annular disk of mass m, that its inner radius be r1 and outer radius be r2. In the case of a circular disk we are having only one radius r, but in the case of annular disk you are having two radiuses, which are the inner radius r1 and outer radius r2. Now we are going to find moment of inertia about an axis passing through the center. So consider the figure. Z dash is the axis of rotation. As already discussed, moment of inertia of the disk is given by, in the earlier case, that is in the case of circular disk, moment of the mass per unit area of the disk we have written is it as m by pi r square, right? Because there is only one radius. But here it is an annular disk. Annular disk means there will be two radiuses, inner radius r1 and outer radius r2. So your mass per unit area of the disk, that is sigma, will become, instead of this, it will become m by pi r2 square minus r1 square. Okay, so not that difference when you study. Now here also we are assuming that this annular disk is made up of a number of thin concentric rings. Now consider one such ring with radius r and thickness dr. Its area will be 2 pi r sigma dr. Now moment of inertia about the ring about z dash, as per equation 20 it is 2 pi r cube sigma dr. Okay, that is in the case of that thin concentric ring. Now many such thin concentric ring will give you that annular disk. So in order to find moment of inertia of the annular disk about an axis passing through the center, what you have to do? You have to integrate this expression from r1 to r2, that is from inner radius to outer radius. Okay, now 2 pi sigma is a constant, take it outside. Then integral r cube dr is r raised to 4 by 4. Apply the limit r1 r2, 2 pi sigma. This one will be r2 square, r2 raised to 4 minus r1 raised to 4 by 4. Then sigma we have already written that it is m by pi r2 square minus r1 square. Then this expression is written as such. Then here pi and pi get cancelled, 2, 4, it will become 2, see here 2. Here this r2 raised to 4 minus r1 raised to 4 can be written as r2 square plus r1 square into r2 square minus r1 square, right? Denominator is kept as such. On simplification, your answer will reduce to m into r1 square plus r2 square by 2. This is the moment of inertia of the annular disk about an axis passing through the center. Okay, now we are going to find moment of inertia about diameter. Same procedure, we are considering two mutually perpendicular diameters, x dash and y dash. Let ix be the moment of inertia along x dash and let iy be the moment of inertia along y dash. Or we have already discussed, moment of inertia of the disk about diameter will be the same, that is ix will be equal to iy will be equal to moment of inertia of diameter id. Now this is a perpendicular axis theorem, iz equal to ix plus iy. Since ix equal to iy equal to id, you can write this as 2id. So id will be iz by 2. Now the expression for iz you have already derived. What is iz? Moment of inertia of the annular disk about the center, that is m r1 square plus r2 square by 2. Just substitute that value in place of iz. Then you will get your moment of inertia of the annular disk about diameter id as m r1 square plus r2 square by 4. So from this you can understand that once you solve a particular problem, let it be a thin circular ring or annular rod or anything, once you solve one problem. Procedure is the same for all other bodies. The only thing is that there will be some changes in the expressions. Okay, procedure that is applied will be the same in all cases. Okay, so write in a paper and study, then only you will remember. Please do remember to draw the figure in all the cases. Okay, all these are expected essay questions from this chapter. You will be asked to derive like this, that is, derive the expression for moment of inertia about an axis passing through the center and the expression for moment of inertia about a diameter of a annular disk, or it will be they will ask you to derive of a thin circular disk, like that. This is a sure question. You will be asked to derive moment of inertia of any of the bodies. It can be thin rod, or it can be annular disk, or it can be circular disk, or like that. Okay, so write and study the proof, explanation as well as figure. Okay.